Hello, everybody. Again, this is Mr. Boswell in the Nature Rocks studio. Today, we're going to talk about polyatomic ions. And I need to mention a couple of things. You probably need to watch all three of these videos if you're going to be able to work all four of the worksheets, which are coming right after you get these videos. They're located on my YouTube channel, Joseph Boswell, and that should get you right there. There's a couple of other things made a couple of years ago there. You can take a look at those. Primarily, it'll be the ones that are most recent. And I'm trying to label them in such a way that you might be able to tell what's going on. All right, so today we're talking about polyatomic ions. And first of all, let's make sure we know what an ion is. We talked about, once again, sodium. Sodium loses an electron and becomes, you know what I just discovered? I just discovered I haven't shared my camera, and so you don't have anything. Live television, you know, what can you do? All right, here we go. There's my, yeah. Here we go. Flower bed that needs cleaning out again. There we go. All right, there's sodium. Yeah, live television, you know, what are you going to do? All right, so there's sodium. We said it loses one electron. And no, we're not going to go back through all of that stuff again, but when it loses that electron, okay, it becomes an ion, a positive ion. Right. And then when chlorine gains an electron, it becomes this, and this is an ion as well. So atoms with charges on them. This is about as simple definition as you can get. But there are those atoms or groups of atoms. For instance, if we were to look at chlorate, and this is covalent bonding here. Let's put this here. We might as well go ahead and look at perchlorate. This is not important for today's lesson, but it might be important to understand what is going on or some of the things that are going on. So let's put these electrons there. And this goes back to when we were looking at tetrahedral and trigonal pyramidal and all of that stuff. These are covalent molecules. We'll put a circle there and we'll put a hydrogen. Okay, so without going into too much detail, these are all covalent bonds. This is a tetrahedral arrangement around the chlorine there. And every once in a while, something comes along and takes that hydrogen away from this group of atoms. And the formula for this is HClO3. Okay, oops, there's 4 oxygens there. Okay, and this is perchloric acid is the name of the compound. Once again, not that important today. All right, let's move on. Every once in a while, something comes along and takes that electron or takes that hydrogen away. And these electrons stay where they were. So the hydrogen goes off somewhere, but a funny thing happens. It leaves its electron with this group of atoms here. And it goes off on its own, and it has a story, an interesting story as well, but it's gone now, let's say. And it leaves its electron behind. And this whole group then picks up a -1 charge. This is a group of atoms. It's the same charge that's on that chlorine right there. Okay, it's a negative charge, but it's a group of covalently bonded atoms, and they have one extra electron. See, all of these other electrons that you see, even the ones in the bonds, those all have protons that balance them off. The proton that to zero, the proton that's balancing this one off, leaves when the hydrogen leaves. And so all that's left of that hydrogen is that extra electron. And so the whole group gets a -1 charge. All right. So the way we write this thing is we write ClO4 -1. And formula-wise, as far as writing formulas would be concerned, it's going to be the same character, the same behavior in writing formulas as that chlorine up there. Okay. So this is called a polyatomic ion. Polyatomic ion. Okay. Because it's a many atom polyatomic, many atoms involved in a polyatomic ion, or in an ion, so that's a polyatomic ion. All right, let's talk a little bit about what happens with that hydrogen, because that could show us the other kind of polyatomic ion. The hydrogen, in a process that's way beyond what we want to do today, will combine with the water molecule, because this all takes place in solution. It becomes H3O. So what that looks like, here's the, let's put a hydrogen there, and a hydrogen there. Okay, so this hydrogen connects, but notice it did not bring the electrons that are a different symbol. That comes from hydrogen. So that hydrogen brings in an electron, and the oxygen brings in an electron to that covalent bond there. And so each atom donates an electron to that covalent bond. But over here, the oxygen donates both electrons. And that's has a special name that once it's called a coordinate covalent bond, but once again, not in today's lesson. But in case you ever hear it, you can say, I heard that before. All right, so this is a coordinate covalent bond, or another covalent bond. And where's the proton, or where's the electron that it used to have? Well, it's back on that other ion. Here it is right there. Got my picture in the way there. Right there. There it is. All right, so it leaves its electron, and then it goes over here and attaches something. Attaches to this water molecule, but it doesn't have a proton to balance that, or it doesn't have an electron to balance that proton off. And so this polyatomic ion becomes positive. So this is a positive polyatomic ion. And there are other polyatomic ions. There are many of them, as a matter of fact. And I have this that I ran off from the internet. Hopefully it's okay to do this. But here's a list, a really nice list of common polyatomic ions. And there is the one we just looked at. That's perchlorate. It was perchloric acid, and IC changes to ATE, and it becomes a polyatomic ion. And then there's some cousins of it. And you see up here, here's bromine. It does the same thing. There's perbromate, and it has the same set of 4 ions. And then here's iodine, another halogen. Okay, all of these ions, or all of these atoms, are in the same family. And this group has the same 4. All right, here's some other real common ones. This is nitrate and nitrite, and those are real common. Permanganate is common. Bicarbonate, sodium bicarbonate, that's the baking soda polyatomic ion. And then here's carbonate. Carbonate is a real common polyatomic ion. Sulfate is real common. There's my blue jay. Okay, over here, here's some other, but notice these have a 2 with them, a -2 charge. So they have picked up 2 electrons extra. And there's a mosquito. All right, and then here's phosphate. These are -3. These are -3. And then here is ammonium. Ammonium is another positive polyatomic ion, like the H3O that I showed you. All right, so those others, like the sulfate, there are 2 atoms of oxygen here that have an extra electron. So that whole group becomes -2. All right, what I'm doing here is that, to me, that looks like it's behind self picture. I'm watching myself as well. And so when I'm doing this, I'm trying to get it out from behind that little square that has me in it. And I don't know, maybe I can find out. One of y'all can shoot me an email or something to tell me whether that square is interfering. All right, and then here's phosphate. This is sulfate, by the way. And here is phosphate. These oxygens are similar. And this one has 3 extra electrons. And so its formula is PO4 -3. Okay. So the nice thing is these ions behave the same when you're balancing charges in compounds. There's just one little thing you have to be careful with. And let's go to here. All right, so the nice thing about this section is you're going to have this polyatomic ion sheet or another one like it. And in some years, I teach my students how to decide what these names are without looking at a list like this. But for this year, certainly, you'll be able to use this chart or one like it. But this is a really nice one if you want to stop and screenshot it or something like that and run it off, and then you can use it. All right. So looking at some of those polyatomic ions and compounds, We'll go back to sodium here. Real common atom and real common ion. We know that it gets a positive 1 charge. The other day, you remember, here it is, it's in the positive 1 column. Then when it reacts with one of these polyatomic ions, for instance, let's use chlorate to start off with. And this is chlorine now, that's an L, it's not an I. Okay, this is chlorate, it's a negative 1 charge. When we put those together, we end up with a formula that looks like this. We just write them right beside each other. They cancel, the charges cancel, just like we did with chlorine. Okay, so this became sodium chloride. Okay, got it? All right, so you can see it balances exactly the same. You just kind of have to get used to seeing a group of atoms over here instead of just one. Now, be real careful. This negative 1 here, negative 1, that's not a charge of negative 3, and that's what you have to get used to. That's what you have to be careful with. Whatever comes in off of this chart, see that group of atoms right there is negative 1. It's not negative 4. Okay. This group over here is negative 3, not negative 12. All right. This is not negative 8. This is not negative 14. Whatever charge you see there, that's the charge you use. And you just have to ignore those little subscripts when you're balancing the charge. All right. So this compound is balanced, and this is by name. This would be sodium. And you get the name off of the chart. Chlorate. So there's that root word again. And this time we put A-T-E on it. The other ending that you see sometimes is I-T-E. All right. So there's my sodium chlorate. Okay, so what if we had calcium, which is positive 2? Calcium is positive 2. We put that with chlorate. Here's what I do. I like to, and I let my students do this. You got to do something. This is kind of like training wheels. You got to do something to teach yourself to ignore that 3 right there. You can't not write it. You have to write it, but you don't want to look at that 3 when you're balancing charge. So put a parentheses around it. Right, and then put a negative 1 on the outside. That way, you're just looking at the charges for each one, and you can see that this charge balance isn't 0. This is a positive 1 charge balance. So what we have to do then is we have to have 2 of these chlorates. And you can do it this way again if you want to start off with. It takes a lot of time though if you're going to continue it. And when we do 2 of those, we end up with a positive 2 and a negative 2, like so. All right, so over here, how do we write that? Well, we write CaClO3, leave the parentheses, and we put a 2 on the outside of the parentheses. These are subscripts now. Write them low. Don't write it even, write it low. In fact, I could put that one a little lower, like that. Okay. And this is calcium chlorate. Calcium chlorate. Okay, so it's just the name of the element that's with it and the name of the polyatomic ion. All right. Notice we didn't use a parentheses here, but you could use one temporarily if you wanted to help you balance the charge. And then if you don't need but one group here, just get rid of the parentheses. And in my case, I don't really care if you leave the parentheses, but you're not technically supposed to. Okay. So let's get another polyatomic ion group going here. Let's try potassium, which is in the same family as sodium. Here it is. It's +1. And let's put that with something that has a -2 charge. Carbonate would be a good one. CO3 -2. So over here, we could say positive, or we could say potassium and carbonate. Here's my +1, here's my -2. I didn't give myself enough room there, so. Okay, so it's -2, this is +1. You can put these training wheels in here. And we can say, no, see, don't look at anything inside the parentheses this way. You can say +1 and -2, so let's put a 2 right there. Or, if it's going too fast, we could say this. And that adds up to +2, and this adds up to -2, which is equal to 0. Then my formula would be K2CO3. I didn't need but one carbonate this time, so I don't need to put a parentheses. All right, so this would be potassium carbonate. Over here. Let me give you some to try. And what you can do is you can pause the video, work it, and then come back in and watch me do it and see if you get the right answer. Okay, so let's put aluminum. Where's aluminum? I'll let you do all of this. So here's aluminum over here, right? And then here is, let's put it with Let me get another. Let's go with nitrate. Okay, so if you don't have a polyatomic ion chart, I'll show you that one right there. There is a really nice one in the book. You have a copy of the book handy. And I have that page written down. It is page 268. So you can get in your textbook, page 268. Okay. But here's nitrate, NO3, -1. So see what you can do with that now. And then you can come back and watch me do it. Pause the video. All right. So aluminum, as we said, is over here, and it's a +3. And then nitrate from my polyatomic ion chart. You have to be careful now, that's an ATE. See, the ITE is a different ion. So make sure you watch those endings there. Okay? Really important. It's like getting the incorrect verb or something in a sentence, or your subject and verb don't agree with each other in person. So be real careful with that. But this is ATE, so that's NO3. It's -1. Right, well, let me run one similar to it. If we were combining aluminum and chlorine, which is chloride, of course, when it becomes an ion, you see chloride is -1. The chlorine ion is -1. So what we did before, that, got a little wind today, and we said, well, that's chlorine with, all of those add up to -3, and this is a +3. So that's going to cancel to 0, and my formula ends up as AlCl3. All right. This works exactly the same way. The charges balance exactly the same way. I have to have 3 of these to get my balance. And you can also do the least common multiple of 1 and 3, which is 3. So you have to get them both equal to 3. So since the aluminum is already 3, then you're going to have 3 NO3s to get up to a -3. And this formula then would be AlNO3. Let's put parentheses in 3. The difference there in this one and that one is that this one you don't need parentheses because there's only one atom there. This one, people will get confused, I'm afraid. They do every year. This is not -3, it's -1. And you have to have 3 of them to get a -1. So that's the reason I'm saying when you're balancing these, if you need to get them right, use those training wheels. Okay, so the least common multiple of these two numbers is 3. So I've already got 3 there. There's an understood 1 subscript. And let's put a 3 over here. And if you saw this in a book somewhere, it wouldn't have those charges. It would look something like that. Okay. How many of you got that right? Raise your hand. How many of you raised your hand? All right. Let's try another one. Okay, to give you a previous example, how we did something else. When we had gallium, or let's use aluminum again. Aluminum is +3 and oxygen is -2. What did we do here? The least common multiple of that is 6 for those two. You could also use the crisscross method. But in order to get that to +6, I have to put a 2 here. In order to get that to -6, I have to put a 3. So when we have something that's +3 with a polyatomic ion, polyatomic ion like carbonate or sulfate. Sulfate's a real common one. SO4. See, if you don't ignore that 4, this is going to get really kind of mixed up. But here's our negative to +3, sorry. Here's our +3 and our -2. Use your training wheels. Here goes the wind again. Let me clamp that down. Okay, use our training wheels if we need to. Here we go, +3, -2. Common denominator, or at least common multiple there, is 6. And so we'll put a 3 outside the parentheses and a 2 here. And so if you saw that formula written in a textbook somewhere, it would look like this. Formal writing don't usually include the charges after you get the formula, but you can pretty much do what you want to. Case, you can leave them there if you want to, or clean up your formula. Just be careful and get your subscripts written the same way. All right. So one other thing, let's look at, before I say one other thing, let's look at one of those positive polyatomic ions. There's only 2 of them that we use, and in most cases, the hydronium that we looked at earlier is not used in formula writing. But ammonium is real common, and it's one of those that starts out as neutral and picks up one of those hydrogens that doesn't have its electron, and then the whole group becomes +1. Okay. If we wanted to put that with something like chlorine, then we could see, use the training wheels if you need to. So they're done the same way. The positive ones are done the same way. There goes my sheets. Clamp it down too. All right, so they are done the same way. And if we clean that up, it would look like that. So if you don't need but one of a polyatomic ion, it's better to get rid of the parentheses. Okay, but if we had, rubidium, which is another one of those alkali metals, and we put it with, say, sulfur, which is -2, we would end up writing Rb2s. So what if we put this with sulfur? Okay, you can stop your video and come back when you finish. All right, so we end up with NH4. Let's put our training wheels on. And we need 2 of those. Gives a positive 2 and a negative 2. Remember, we have to have the same number of electrons lost as gained. And so that 0, very important. Okay, so how do we write this? Well, we have to leave the parentheses because we have more than one of them. And then we write the sulfur right behind it. And this is ammonium sulfide. Okay, and this one was ammonium chloride. And notice, when you only have one other element that a polyatomic ion is with, it's treated like it was a binary compound, and it still gets the "ide" ending. All right. So if you have polyatomic ions with those elements in the middle here that have many oxidation states, they're done exactly the same way. It's just that if I wanted you to write copper with a polyatomic ion, I would have to tell you which one I wanted you to use. All right, so this is, I would say, copper 2, meaning use the positive 2. And then this one would be copper Roman numeral 1. And again, if you can remember to use the parentheses, that's always better. So when we put these with polyatomic ions, we balance the charges, training wheels, that balances to 0. And then this one, we have to have 2 coppers. Okay, so the name of this one would be copper 2. And then the name of the polyatomic ion, sorry, I'm off the screen here, sulfate. And this would be copper Roman numeral 1 sulfate. Okay, so just kind of combine rules there. Let me give you one more and see how you do. And then that'll be it for this video. What if you had something like drawing a blank. Let's do calcium plus phosphate. Okay, remember now, look for the one that has ATE. Okay, so you can pause the video to get that written down. I think you can still see, pause the video and work that problem, and then come back and let's see how we did. Okay, so I see here phosphate is a -3 charge on it. And remember that ATE tells me I'm using the one with 4 oxygens. So this is PO4. And I can use my training wheels here. If you get to the point where you don't need those training wheels, you're doing great. And then calcium. Calcium is +2. So this is my least common multiple thing, or the crisscross method. I need to get them both equal to 6. So I'm going to need 2 of these, 3 of these, sorry, to get up to 6. So that's +6. And then 2 of these to get up to 6. And that cancels to 0. So my formula then becomes that. Okay, so how many of you got that right? I got some more of you. All right, well, once again, I'm coming to you from the Nature Rocks studio, and staying safe. I came up with a new word. Share it with you. Stay safe. If you combine those 2 words, you get safe. So stays, everybody. See you next time. And remember, it's kind of a good idea to watch all 3 of these videos, which you probably would have done better hearing at the first one, to do all 4 of the worksheets. So take care, and we'll see you next time. And it takes me a little while, of course, to get this video to shut off. So let me see what happens. There we go. And stop recording. Goodbye. I think I'm still here.